Assalamualaikum and hello everybody. Welcome back to KNC 2123 heat and mass transfer. So we're still on heat transfer, and this is the second part on steady state heat conduction. Okay, and particularly we're going to look at thin surfaces. All right, so when you heard the word thin here, so yes, it is the fin that you imagine in your head. It is something that is extended from the surface or something attached to a surface um, that actually is used to uh, uh, aid in the heat transfer from the surface. Okay, all right. The learning outcomes for this lesson is first for you to be able to analyze thin surfaces and assess how efficiently and effectively. So there are two parameters here: if efficiency and effectiveness of fins in enhancing heat transfer. All right. So you must know that the purpose of using fin is to enhance heat transfer from the surface, and then we will see later on why do you need this, in what case, and then and how well it can perform this task. And then you should be able to solve multidimensional practical heat conduction problems using conduction shape factor. So you will see that there are a lot of cases that actually can be approximated as fin, right? Or there are a lot of fins configurations, and then in practical use for heat conduction. So there is a simple way for you to do that, to do analysis on that system to solve for the heat conduction. All right, so look at this image here. These are the examples of fins. So usually you'll see this in electrons, right? Because they also conduct electric through the component, and it generates heat, isn't it? So if you want to keep the integrity of this component, you must release the heat efficiently, right? So because if it is too small, so the surface area is small, isn't it? So you need to extend the surface so that more heat can be released, right? Now, because we're talking about surfaces, so we're actually looking at convection heat transfer at the surface, right? So the heat is conducted within the body, and then from within the body to the surface, and then from the surface to the environment. So we can use Newton's law of cooling as in this. All right. So you've seen this. Okay, so from here, from this equation here, we can see that there are two ways for you to increase the rate of heat transfer, to increase the Q. Is first to increase H here, heat transfer coefficient, and then secondly to increase the surface area, right? So for fins, we are actually looking at increasing this A here, right? The surface area. Now, it is important for you to be able to develop a fin equation, and right. So, still under steady state condition, the energy balance from this fin. So this is called an element, right? It can be written like this. So the rate of heat conduction into the element. So the rate conduction into this fin here. So for this is the body, right? So this is the fin, one fin, right? The conduction into this fin is equal to the rate of conduction from this fin plus rate by convection from this fin, right? So there is still conduction here going to this direction, and then there is also convection at the surface of this fin. So you see the surface of this fin. So around this area. So we can take this is as the surface. So this is the surface on the top surface, and then we have at the bottom, and also at the sides here, two sides here, right? And also at the tip here. But usually the tip here is too small that if you don't include it also, it's just okay, right? So it can be negligible as well compared to the surface on the top and at the bottom here. Okay, so that is why if you see here, the area here, this is area, is given by perimeter times the length here, right? So this is your, so let's clear this one first. Right. So this is the perimeter. You see, this is the perimeter, right? And then as x is increasing or going to approach the total length of the fin, right? So the area is changing, isn't it? So for example, at here, the surface is only here, isn't it? So that's why you take the area as the perimeter times the length here, the x here. Okay. So when you increase to here, so all of this become the area for the fin. Okay. So if you see that why we are using perimeter is because of different shape. For example, if this is the rectangular shape, right? So the area is going to be like this, isn't it? Whereas when it is cylindrical, so the perimeter is this. And then you times with the L, the length here. So this is the perimeter. So this is the perimeter for rectangle. Because we only take the surface here, isn't it? Whole surface here. So this is the perimeter. Right? So, okay, so substitute this into this first equation and then divide it by delta x, right? You will get this, okay? And as usual, taking the limit as delta x approaching 0, it will give you this, right? Differential equation. And let's clear this one. So, and then you can substitute Fourier's law into this equation. You can obtain this equation then, right? And then yes, of course, the AC is changing with x, right? The cross section area. So this is this is the same as we did before, right? So if AC and K is taken as constant, you can reduce it into this equation, right? And we take this difference here, temperature at any location within the fin minus the ambient temperature here is as theta here, right? And then this term here is taken as m squared, right? So so m is equal to square root of this. Okay, right. This is just to simplify how do we write this, right? So don't really worry about this. So you can write it like this, knowing that this theta means this, and this m means this, right? Okay, so if you realize this equation is linear homogeneous second order differential equation. So you've learned this in mathematics engineering here, right? With constant coefficient. So this is the simplest form of differential equation that you can actually get the general solution like this, right? You can uh, there are ways for you to solve this, and then the easiest way is to integrate it twice, isn't it? As we've seen before. So you will get the solution is like this in this equation, where you have two constants, right? And then because we know that we have two constants, we need boundary conditions, right? So for fins, we need one at the best of the fin, right? So you have your fin, for example, like this, your fin. So at the best, the condition at the best, and another one condition at the tip, right? Okay. Now, so so at the fin best, so usually you write the equation like this. So at x equal to 0, yeah, you actually have um, uh, the temperature difference from the best, right? All right. So TB is the temperature at the best minus T at ambient. Now, for the condition at the tip, there are four cases, right? So the first one is infinitely long fin. The second one is adiabatic fin tip, and then we also have specified temperature at the fin tip, and then convection from the fin tip. All right, for the first case, the fin is considered to be very long, that the temperature at the tip is equal to that of the ambient. Okay, so you can write the condition at the fin tip as in this, right? So at the fin tip, so the x is equal to L now, right? So temperature at the tip, this is temperature at the tip of the fin. Tip means at the very end of the fin, right? So the difference with this and the ambient temperature is 0 because it's already the same, okay? As you can see from this graph, this is the temperature profile of the fin, okay? So at the best, the temperature is at its body temperature, right? As it goes along the fin, because it's being dissipated throughout this fin surfaces, the temperature reduced, isn't it? So in this case, it is reduced gradually, and then at the end of the end of the fin, the temperature approaches the ambient temperature, right? So, so as x approaches infinity, so this term also infinity, isn't it? So when you put in into this equation, you put it into this equation, this general solution, you will get C1 equal to 0. Okay, and then at x equal to 0, this term become 1, isn't it? then you get C2 equal to the best temperature difference with the best of the tip. All right. Yes, you can prove this by yourself. So you substitute into the general solution, right? So this is the general solution. Let's see from here. So this is your general solution. You can write. Let's write it. Okay. Right, because C1 is 0, right? So 0 plus, and then this C2 is theta B times exponent of negative mx. Okay. Okay. So this one is actually this. So you bring, okay, so like this. So bring this here. So this is actually this. This is theta B here. So you get this. Okay. And then you substitute m. We will see m is equal to this is now, right? So you get this. So this is actually your, and then if you solve, if you solve for Tx, you get this. This is the general solution will give you the temperature distribution within the tip. Okay. So that's the use of the fin equation for you to get the temperature distribution along the fin, right? Now, so you already have the temperature distribution, then you can find the heat transfer from the fin. Right. So how you get this is that you just substitute again the equation. For example, you got this. This is temperature distribution, isn't it? You got this now. So how to find this? Yes, you differentiate this, you will get negative m theta b e mx, right? So you substitute this into here, but because there are two negative here, so the q here you will get k, right? Is KAC, and then because of this m here, HP over KAC times with B, isn't it? So you can reduce this, you will get this, right? So this is the same as this. Okay. Right, so this is the first case. Now the second case is more practical because it is very unlikely that you will have or you will use a very, very long fin, right, in your system. Rather, you will have to assume that at the fin tip there is a adiabatic or negligible heat loss from the fin tip because probably it is negligible, right? The heat loss is probably negligible because of the surface area is negligible. So usually you can exclude the area of the tip, area at the tip there. And sometimes a different shape of fin tips will have no area at the tip, right? No area, like a cone, for example, right? So at the tip there, you don't have to find the area. So we can say that there is no heat loss from the tip, okay? Okay, in this case, you can write your boundary condition as in this, right? So when you include this in the general solution, and then you integrate it, double integrate it, and then to get the constants, you will get the equation like this, right? So I don't know where have you found this. This is hyperbolic function of cosine, right? Or we say this cos, right? Cos. But I think it's fair to recall this. So if you get, you can find this actually. Is equal to exponent of x plus exponent of negative x divided by 2, right? So when you got this from the integration, you can convert it into cos, okay? And then this is the same like sine is equal to of x minus, this is minus 2, right? So we say this as sine h, but how do you pronounce it? It is shine, yeah? With h, shine. So down here is the same. This is actually shine divided by cos, or this one over this one. Okay, so that's why you get this. Okay, so you can do this yourself, and you should know by now how you get this, right? So you obtain this, differentiate it again, and then put it here. Okay. So the third case is that when you know the temperature, when you can measure the temperature at the tip, right? So when you can measure the temperature of the tip, you actually have another boundary condition or temperature difference. That is temperature difference at the tip to the environment. Okay. So this would be the case where the fin is not too long, or maybe it's a short fin, for example, that there is still temperature difference with the ambient. Okay. And then, as usual, you obtain the general solution. You got this, you got shine here, and then differentiate it again and put it into this Fourier's law. You get this equation. Okay. So this case could be considered as a generalization of the case of infinitely long fin where fin tip temperature was fixed at the ambient. Okay. So if you actually substitute this T ambient here into this equation, you can actually get back the solution to the first case. Okay. Right. So the final one is when there is a convection also from the fin tip, or there is a case probably that you cannot neglect the convection or heat from the surface, from the fin surface. So like I said, this depends on the configuration, on the shape of your fin. Okay. So you can write it in this equation. So the boundary condition is the heat conduction from the fin is equal to the heat convection to the fin equal to the heat convection from the fin. Okay, and then you obtain again the general solution. You get this cos and sine here, and then you differentiate it again, put it back into Fourier's law, you get another equation. So different condition will give you different equations from the fin types. Okay. Okay. So in another case, you will also need to express the length required for you to be able to achieve the convection at the tip by using an equivalent length. There is called the corrected fin length. So this corrected fin length is actually an equivalent length where you have an insulated fin tip. Okay, so all right. So let's see two conditions. So the first one, when we say there is a convection at the fin tip, right? So and then the second one is when we say there is no heat loss from the fin tip. So how much length is required for the second condition to achieve the same heat loss or heat transfer with the first condition, right? So because we know that when there is no heat loss here, you need additional surface area to remove the same heat. Okay, so we call this corrected fin length, right? So you probably need this to compare, you know, the cost for the fin, right? So if you have a longer corrected fin length, probably you might want to consider a different material, for example, right? And then this also depends on the condition that you have surrounding the fin. Okay. So corrected fin length is given by the actual length plus the cross-section area over P. So AC over P here is the characteristic length, we call it, right? Characteristic length, which is different for different shapes of fin. For example, if you have a rectangular fin, this characteristic length is T over 2, right? For cylindrical fin, this is R over 2 or D over 4. Okay. Okay. We talk about two parameters important when you want to decide whether you want to use fin or not. Okay, so the first one is the fin efficiency. Okay, so fin efficiency is actually it's common with it's the same with the other efficiencies that you have learned before. Is equal to the actual heat transfer rate from the fin divided by the ideal heat transfer from the fin, or the maximum heat transfer that theoretically the fin can remove, right? So this is the case where the temperature there is no temperature difference within the fin. So this is an ideal, very ideal case that will not happen, right? So this is just, we see that this is the maximum heat transfer rate that we will obtain if the temperature throughout the fin is the same as the base temperature. Okay, so you will have a maximum heat transfer from the fin. Okay, so this is the maximum heat transfer, and then the actual is when you embed the this temperature difference, temperature distribution into your calculation, right? So when talking about maximum here, so this is the equation for the maximum heat transfer from the fin. Okay, you just take the base temperature difference with the ambient. Okay, and then you can calculate this by using the equation that you've seen just now, right? And then you can find the efficiency, right? Or in some cases, some suppliers they supply this value, this efficiency value. Then you can calculate this. Then you can directly get this, right? Because you know, for you to know this, to calculate this, you need to know the condition, or you need to make some assumptions, isn't it? There are 4 assumptions that you need to make, you need to choose from, okay, in order for you to calculate that. Right, and so we can actually obtain the fin efficiency for a particular system. As I said just now, we just take the Q fin over Q fin max, right? And substitute back the equation that you have seen before, right? And this maximum heat transfer for the fin, and then you can actually reduce it into this, isn't it? So you can actually see that the efficiency is depending on the properties of the fin as well as the fluid, right? Of the system, you know, for the convection, isn't it? Right. So this is for constant cross section of a very long fin, while for constant cross section with elevated fin, you can put in the equation that you can determine just now, right? And then you can obtain this, right? It's also depending on the same parameters, but on different equation, because you have a different assumption or different case at the fin tip. Okay. So these are the 2 examples for the 2 cases that we have seen. Okay, so you can do this for the others, right? So there is a chart you can obtain, and there are other type of charts, but this chart, particularly for rectangular, triangular, and parabolic fins. Okay. So you can see the y-axis here is for the efficiency, okay, and then the x-axis is for this z parameter. Okay, so there are 2 other parameters that used in this this x-axis. There is this LC here. This is the corrected fin length that you've seen, and then the area of the perimeter. Okay, so for rectangular fin, the LC is given by this, right? And then the AP is equal to this LC times T here. So T is the thickness here. Okay, so for triangular, the LC is equal to the L, and then there's no there's no characteristic length, but the AP is equal to LC times T divided by 2. So the T is at the base here, right? So this is actually the same. This is also at the base, okay, the T. Whereas for parabolic profiles, the AP is equal to LC times T divided by 3, okay? Right. So when you have any of this, maybe you have Z, or you have the efficiency, and then you know which type is it. So if it is rectangular, you follow this curve. If it is triangular, you follow this second curve that it goes here, right, in the middle here, and then at the very end here we have parabolic. This is parabolic going here. Okay, so remember the middle here is for the triangular, and then the outer here is for parabolic. So you can just find the value, okay, from by following this curve. So there are other resources for you to find the efficiency of the fin, or you can actually just calculate them, okay? Right, so the second parameter for fin is the effectiveness. So you have to remember there are two, the efficiency and effectiveness. So this is different, okay? The performance of the fins is judged on the basis of the enhancements of heat transfer relative to the no fin case. So this will tell you whether how good it is to have the fin compared to when using no fin. Okay, so the fin effectiveness is given by the Q fin here, the heat transfer from the fin of base area AB, okay, divide by heat transfer from the surface of area AB. So so you see there is no fin here. So what is the transfer? And then when you add the fin, what is the transfer? And how much it is increased is actually the effectiveness. Okay. So yes. Okay. So you have to note that the thermal conductivity K of the fin material should be as high as possible. So this is the case where you want to design a fin. Okay, so you must choose a material that has a very high K. Okay, the ratio of the perimeter to the cross-sectional area of the fin, that is P over AC, should be as high as possible. Okay, so this is the heuristic design for fin. Okay, how do you decide on the dimension of the fin? Okay. The use of fins is most effective in applications involving a low convection heat transfer coefficient, right? So people only use fins. It is only economical if there is a case of low convection heat transfer. Okay, because so it says here it's more easily justified when it is more economical. Okay, when the medium is a gas, right, instead of a liquid, because gas has lower convection heat transfer coefficient, and the heat is transferred by natural convection instead of forced convection. You will see natural convection has lower heat transfer coefficient. Okay, so in the case for lower convection heat transfer coefficient, then it is justifiable to use fin. Okay, so this will give you a higher fin efficiency. Okay, so if it is already high, right? If it's high here, so you get low here, isn't it? So if this is already high, you get lower efficiency, effectiveness, sorry, lower effectiveness. All right, so because we are dealing with many fins at one time or in one system, is usually the case, right? It's common to check the overall effectiveness rather than to check individual effectiveness of each of the fin. Okay. So how do we do this? First, we find the total rate of heat transfer from a fin surface. Okay. So this equal to the Q from the surface that has no fin plus the Q from the surface that has fins or from the fin. Okay. So you must calculate the area of the unfin. Okay. The area of the unfin here is only this section. It's only on this part. So this is the unfin. So the area of the unfin is the total area, for example, of this square area here. You minus, example, if you have 3 fins, 3 times this, because this area at the base here has already been taken by the fin, right? So you have to minus this section here, these 3 section, these 3 areas. So this is the unfin area. Okay, so you got this. And the overall of the effectiveness is the Q total fin here divided by the Q total no fin, right? So there are 2 things, unfin and no fin. So you have to remember, unfin is the surface that has no fin, while no fin is the surface when there is no fin at all. Okay, when there's no fin at all, consider it to be only, you see here, you don't minus to anything, right? So because we want to see how much it is compared to when having no fin. Okay, and then you got this. So the overall fin effectiveness depends on the fin density, the numbers of fins per unit length. So if, for example, you take just 1 unit length, how many fin is inside it, for example, right? As well as the effectiveness of the individual fins, right? Okay. So the area of the fin is the area on the top and bottom here of the fin, right? So that's why it is 2L times W here, and then plus the area of this tip here, right? But this is sometimes negligible, so you can actually exclude this, right? Also approximated as this for 1 fin. Okay, or you can have the perimeter times with the L. Okay, that's for 1 fin. And then if you say you have 1,000 fins, so the area total is equal to 1,000 times area of each fin. Okay, so you use this in here. So that is why the overall fin effectiveness depends on the number of the fins. This is number of the fins, this n. Number of the fins, as well as the effectiveness of the individual fins, as well as the effectiveness. So we take that if this is effectiveness is the same, for example, 80%, so overall it's also 80%. Okay. Now, so this problem, you will have to find the proper length of a fin. So this is also a design problem in order for you to decide how long is your fin. Okay. So an important step in the design is to determine the appropriate length of the fin once the fin material and the fin cross-section are specified. Okay, so first you have to, which means that you will have to specify the material first and also the cross-section. That is from the probably the area, right? The temperature drops along the fin exponentially, right? So the temperature drops exponentially and approaches the environment temperature at some length. Okay, the region near the fin tips makes little or no contribution to heat transfer. Okay, so at one point you will see that there is no more heat that can be transferred to the surrounding because the temperature already reached the ambient temperature. Okay, so that's why you have to determine this, or this to identify the cost-effective length of the fin, right? So for example, you might just want to knit until here, for example, okay? Might just knit until here, then that's fine. So you don't have to waste your material for a longer fin than this, okay? All right, so yeah, as you have seen, there are a lot of repetition on this ML term, right? So some calculation have been made, an approximation actually, from having this number of ml to what heat transfer ratio compared to the long fin, which means that if, okay, let's say, if you have ml equal to 5, this is where the case that you actually have a very, very long fin, okay? So if you have ml equal to 1, heuristically, it offers a good compromise between heat transfer performance and the fin size. So this is more preferable, okay? So this heat transfer ratio is taking the heat transfer from your fin to when you or when it is assumed that you're having a very long fin. Right? This is to decide. It is for you to decide whether your fin is actually very long or not. Okay. So when it is when it reach 1 here, which means that you actually have a very long fin. Okay. This is the second outcome for the lesson. That is for you to be able to solve a multi-dimensional problem related to fins, right? So in practice, they are 2 or 3 dimensional and involve rather complicated geometries for which no simple solutions are available. All right. So we can simplify this when we take a constant temperature T1 and T2, and then we say that it is steady state. Okay. And if even though you have multi-dimensional, but you have steady rate of heat transfer between these two surfaces, you can actually get an equation in this form: Q equal to S K to the times with the temperature difference of the two surfaces. Okay, where S is called conduction shape factor. Right, so the dimension is length. So this in this table you can find specific equation to find S, and then you can plug it in into this equation to find the value of Q. Right. For example, if you have equally spaced parallel isothermal cylinders, right, several cylinders spaced equally here with W distance here. Buried in a semi-infinite medium, or for example, like in a soil or something, or under the ground, for example. So you can calculate S using this equation, right? And then you times it with the number of cylinders you have, right? And then put it in here. Okay. So any of the case that you have here, you can use this S and then put it into this one. So this is a simpler method for you to solve more complex geometries of things or cases, right? So they actually can be approximated as fins. Okay. All right. So to end our lesson today, let's recap all of what we've learned. Okay. So what is the reason for the widespread use of fins on surfaces? Yes, to increase the heat transfer rate from the surface, right? To release more heat, isn't it? Okay, what is the difference between the fin effectiveness and the fin efficiency? Right, I think you can answer this yourself. You should be able by now, be able to differentiate the two of these parameters by now, right? All right. Hot water is to be cooled as it flows through the tubes exposed to atmospheric air. Fins are to be attached in order to enhance heat transfer. Would you recommend attaching the fins inside or outside the tubes? Why? Right. So we know that inside the tubes is water, right? And then we want to enhance the heat transfer. So do you put the fin inside or outside? So for example, this is a tube. So do you put the fins inside, outside or inside? So inside here you have water, right? So do you put it inside or you put it outside? So you know that fin effectiveness will be higher if you apply it to gas instead of fluid, because gas here outside here and the ambient is gas has lower heat transfer coefficient, convection heat transfer coefficient, okay, compared to a liquid here, because there is flow inside here. There should be higher heat transfer coefficient, and then you enhance the lower one that is at the outside part. Okay, so that's why it's better to put it outside the tube. Okay, hot air is to be cooled as it is forced to flow through the tubes exposed to atmospheric air. Fins are to be added in order to enhance heat transfer. Would you recommend attaching the fin inside or outside the tubes? Why? When will you recommend attaching fins both inside and outside the tubes? Okay, now in this case, it is hot air flowing inside this, not hot water. All right. So if it is hot air, then where should you put the fins? Is it inside or outside? Okay, I need you to answer this on ellip. Okay. So this is number 1. This is number 2. This is number 3. Okay. So you have to have 3 answers. Right. Consider 2 fin surfaces that are identical, except that the fins on the first surface are formed by casting or extrusion, whereas they are attached to the second surface afterwards by welding or tight fitting. For which case do you think fins will provide greater enhancement in heat transfer? So the first fin is being formed during the casting of the material, right? So you have a mold for this tube, actually together with the fin, the mold, right? So you already have fins embedded within the body of the surface. Rather than the second case, you have a tube and then you weld the fins on the surface. So which one do you think will provide greater heat transfer enhancement? Right. So it's this one, isn't it? Because of, if you still remember this. So when you extrude it to in the mold of the surface material, you will have less air gaps, for example, right, or gaps between the fin and the surface, whereas this welding or fitting is depending highly on your skills and how perfect you do the job. Okay, but still there are gaps, probably air gaps, right, in between the surface and the fins that actually will give you another resistance to heat transfer. The heat transfer surface area of a fin is equal to the sum of all surfaces of the fin exposed to the surrounding medium, including the surface area of the fin tip. Under what conditions can we neglect heat transfer from the fin tip? Right. So I talk about this in this video. You can see that when the fin is too long, or when the surface area of the fin is too small compared to the total surface area of the fin. Or, for example, if you have a tip fin like this, right, rectangular, so at the tip here is very, very small, isn't it? Okay, does efficiency and effectiveness of a fin increase or decrease when the fin length is increased? Right, you know, in the efficiency is equal to Q fin over Q fin max. Right, so this Q fin max is actually equal to HA fin TB minus T surrounding. So when you increase the length, this also increase, and then this will increase, and then this will decrease, right? As for the effectiveness, is the other way around, isn't it? Because the effectiveness didn't take into account the area of the fin. It's only take into account the area of the base. We say here no fin. So this is only H area of the base only, T base minus T surrounding. So if you increase the fin length, this will not be changed, but this will change. Okay, so this will increase. Okay, so that is all for this part, and then I will continue on the examples in the next video. So thank you. Don't forget to answer this in your ELIP for your attendance. Thank you.